Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at mappings, piecewise functions, and piecewise transformations. So to begin with, it is worth defining a mapping. A mapping is basically any real function. So by a real function, I of course mean any function which takes in a real number and gives out a real number, right? Which is the vast majority of functions that we see on the A-level syllabus. It is actually worth mentioning a remark, which is to say the word mapping and the word function actually gets used interchangeably, generally speaking. So as to have a slightly better idea of where the word actually comes from, it's worth thinking about what actually a function does. So a function obviously starts with some sort of domain, and it's a set. And using sort of ideas about Venn diagrams, we can represent sets like this. And then obviously it gives us some range, right? And again, it's a set, so we can express it like so. And what we have is we have things in our domain, and then we have things in our range. And of course, what a function does, it takes some input and it sends it to some output. Okay, and it takes some other input and it sends it to some other output. So this sort of graphic is a common way of describing functions. And in this sort of a picture, you can start to imagine why the word mapping starts to come about, because what's happening is we've got this input being mapped to this output. And likewise, for every input that actually the function's going to act on, it's going to map it to some output. Okay? Perhaps I should say that this is a common schematic describing mappings, or functions indeed. The last remark worth saying is actually there are different types of mappings. There exist different types of mappings. And we will go on to take a look at a few of them right now. So in fact, there are four main types of mappings, four types, and they are called as follows. So the one of them is called one-to-one, another one is called many-to-one, and then a third is called one-to-many, and unsurprisingly, the fourth one is called many-to-many. So let's think in terms of a schematic what a one-to-one mapping would actually be. Well, in all of these cases, obviously, we're going to have some sort of domain, and we're going to have some sort of a range. And so using the schematic we've already sort of seen, we're going to have these Venn diagram-like objects, and we're going to have inputs and obviously outputs. A one-to-one mapping is basically literally what the words actually say. So it means one input only gives you one output, right? One input only gives you one output. Okay? And again, one input only gives you one output. But of course, the important thing here is each input actually gives you a different output. Okay? And this is where the many-to-one mapping is actually different to the one-to-one mapping. So what can happen in the many-to-one mapping is as follows. So again, we have some sort of a domain and obviously range. But in this case, what happens is our inputs and our outputs do something slightly different, which is we can actually have two different inputs mapping to the exact same output. And that's perfectly well defined. Okay, why is it well defined? Because if we go back to the definition of a function, all it says is that each input should have one output. So this input has one output, and this input also has one output. And that's perfectly well defined. So a many-to-one mapping is actually also a well-defined function. The third case is, of course, one-to-many. So again, we're going to have some sort of a domain, and we're going to have some sort of a range. Perhaps it's better to lay everything out like this because it then gives me enough space to write everything down. So again, so we go back to this. So we have some domain and we have some range. And in this case, we're going to have things in our domain as before, and we're going to have things in our range as before. But now we're going to have something slightly different, which is one input is actually going to give me many outputs. So that's one output, right? And this might be another output, okay? So there might still be something which gives you one output for one input, but the point is if there is at least one object, one input, which gives you more than one output, then the thing you have is actually a one to many. So let me write that down. And of course, needless to say, this does not satisfy the definition of a function. So I shouldn't even say it's a type of mapping, given how we've defined mapping, but I hope that's actually clear. This case here, one to many, and in fact also the many to many, is only been mentioned for the sake of completeness, right? So perhaps I should write that down, which is these things here are functions, and maybe in a different color, these things here are not functions. So of course, since in a well-defined sense, every domain value should actually have an output, and from my diagram here, my schematic, that domain value doesn't seem to have an output. So perhaps I'll just say I don't want to actually count that in as a domain value. Otherwise, I'm going to have to draw another arrow. There's too much stuff there already to draw over. So let's consider the last case, which is many to many. Okay, so again, we're going to have some sort of a domain and some sort of a range. And this shouldn't actually surprise you. So we're going to have inputs and outputs. And now we're basically going to have each input maybe giving you one input, but it could actually give you two outputs. Okay, and the interesting thing here is you can actually have, because it's many to many, you can have many inputs giving you the exact same output. Okay, so you can now see how qualitatively the many to many is different to the one to many. So the one to many would allow for one thing to go to multiple things here, but it doesn't allow for multiple things here to go to the same thing here, right? But in the many to many case, it allows of both those cases. So one thing here can go to multiple things here, and multiple things here can go to one thing here. Just so it's crystal clear, I'm going to go back and write all of these definitions in words, okay? So one-to-one is basically one input gives one output. Many-to-one is many inputs give one output. One-to-many is one input gives many outputs. And many-to-many is perhaps a better way of saying it, rather than saying many inputs give many outputs, is to say many inputs give one output, and one input gives many outputs. At this stage, you might think to yourself, why are we classifying mappings instead of all these different categories, right? And you might say two of the cases that were actually described here, or one category here, is actually not even a function, right? And my answer to you would be it's because we want to build up the theory of functions in some sense to be able to do some interesting and useful things with them. And it works out that it's really useful to categorize functions in general in sort of these categories, and then you can say certain things. You can say that this category is going to have certain properties and this category is going to have certain other properties, okay? But you will see more on that as we start to sort of develop the theory a bit more and then look at some questions. Before moving on to look at piecewise functions, it is worth looking at an example of all the various type of objects we've actually discussed, which is one-to-one, obviously many-to-one, one-to-many, and many-to-many. So a good example of a function or a mapping which is one-to-one is actually any straight line, okay? And you can sort of go away and think about this maybe, and it's actually quite clear from this picture that for each input, you are only going to get one output, right? And it's actually a bit more significant than that, which is written here, which is every input has a different output, and that different part is actually quite important. That's what makes a mapping one-to-one as opposed to just many to one, because for many to one, each input is only going to give one output, but the point is that output doesn't actually have to be different in the case of many to one. So let's have a look at this. It says every input has one output, but some inputs have the same output. Okay, so as long as there's more than one input which reproduces an output, then the mapping you have is actually many to one, which is obviously very different to one to many. So in this case, we see that there is one input, right? An example might be, say, x equals 9. So you put x equals 9 in, or maybe even x equals 8 actually. You put x equals 8 in, and you get 8 plus 1, which is 9, and you take the square root of that, and you get positive and negative 3. So one input actually gives you two outputs, okay? So some inputs have more than one output. And lastly, something which is many to many. So technically, this is not really a function, but we need to be slightly careful about this. There is more on this in a video on, I believe, parametric differentiation in the differentiation video series. So if you want to take a look at that, do feel free to go take a look at it. But it's probably a little bit advanced if you're just starting out in the second year of your A-level maths to look at that video. But anyway, so in this case, we can see that I've got two different sort of colored lines effectively, or line segments, and one of them is telling me that for one input, I can have two outputs coming out. And the second one is telling me actually that there are two separate inputs and they're giving me the exact same output. And that's pretty much what I've said here. So some inputs have more than one output and some inputs have the exact same output, right? So that's the characteristic essence of a many-to-many object. So let's move on to piecewise functions. So what is a piecewise function? Well, in essence, a function is a piecewise function if it can actually be split up into pieces, right? So let's take a look at the definition. So a function is said to be piecewise if it can be defined by listing two or more functions over different parts of the domain, right? So let me maybe write a remark to be able to explain what the definition is trying to say. So imagine we've got some function f of x, and it's actually defined by using two separate functions, f1x and f2x, right? And what we might say is if x is, say, less than some number, then use f1 to be able to define the function f. And if x happens to be bigger than or equal to some number, then use, say, f2 to be able to define f, right? So the function f actually is defined by two separate functions, and which function we choose depends on which domain value we're actually going to put into the function in the first place, okay? But of course, the catch is it doesn't have to be sort of two functions. It can actually be a lot more complicated than that. So I could have a function g, and there might actually be three functions. So it might be g1, g2, and g3, right? And we might say x is less than a, and x is bigger than or equal to a, and less than b, and say x is, say, bigger than or equal to b, right? And of course, in both these cases, what I'm assuming is a and b are some sort of given numbers, right? Where a is some real number and it's fixed. And in the second case, I'm saying where a and b are some real numbers and they're fixed. But in saying this, it's implicit that actually this function is defined over the entire real numbers, and that function is defined over the entire real numbers. But you might find that, the function that you're dealing with might actually be a mapping. It might take in real numbers and give out real numbers, but it might only be defined for a portion of the real numbers, right? It might only be defined for x being positive or x being negative or x being between 1 and -1 or what have you. So just be mindful of that, okay? But I hope the definition of a piecewise function is sort of clear. What I should add actually before moving on, which is a piecewise function is actually a function, right? So we can see that quite clearly, say in this case, because f1 is a function, which means anything you put in it's only going to give one thing out, which means for all sort of these domain values, my function f is actually a technical function because this thing here is only going to give one thing out, which means f is only going to have one output, right? And the exact same argument would actually apply to f2, and obviously that's going to apply for x being bigger than or equal to a, which means for x being bigger than or equal to a, my function f is actually going to only give one output, therefore making it a technical function, right? So let's go and take a look at some examples of piecewise functions. So in the interest of time, I've already written out the three examples, and actually they've been chosen to try and highlight all the key ideas, all the key properties that sort of piecewise functions have. So let's take a look at the first case. So we have f of x, and our two pieces are defined here. So the first piece is our function, just our generic parabola, and the second piece is actually a straight line. So the two pieces have been graphed here, and we see them in different color. So we see the first piece is defined for all x values being bigger than 0. So x equals 0 is not included, and therefore the point 0, 0 does not actually lie on that green branch. It actually lies on the blue branch because the second function, y equals x, actually is defined for x being less than and equal to 0. Okay, so the interesting thing about the first example here is the fact that it's actually a continuous function. In other words, you can draw the entire graph of y equals f of x without lifting your pen off the page, right? Case 2 is we're given a function g of x, and it's actually now a discontinuous function. Okay, so if you take a look carefully, it's defined again by two separate functions. So for x being more than 0, y is always 1, and for x being less than 0, y is always negative 1. So if we were to go and graph these, we're going to get two branches. So for x being more than 0, we get y equals 1, and x being less than 0, we see that we get y equals minus 1. And of course, at x equals 0, the output is actually not defined. So neither that point or that point there are actually part of the graph of y equals g of x. And this is obviously discontinuous, right? Because there's no way to go from here and then to go there without lifting your pen, right? So it's a discontinuous function. So I suppose this is probably the first time for a lot of people in seeing a discontinuous function. They might have come across the idea of discontinuity at A level, maybe in the context of integration or in some other context, but this goes to show what discontinuity actually looks like. Let's take a look at the last function. So this piecewise function is actually made up of three pieces. And the interesting thing here is it's not defined for all real numbers, right? So, I mean, this was not defined for all real numbers because in particular, it was not defined for x equals 0. But the point is, other than x equals 0, every other input was actually well defined. But in this case, if you take a look, x is defined for x less than negative 1. So all these x values we've got a function defined on, but then x is not defined for anything more than 270. So we come to anything past 270, and the function, the way it's been defined here, will just not accept any of that as input. Okay? So here, as I say, we've got three branches. The first branch is y equals x squared, and that's the blue part here. The second branch is y equals minus 1, and that's the green part here. And obviously, that's valid for inputs between minus 1 and 90. So that x value there is minus 1, and this x value here is 90. And then the last branch is actually a tan function, and we only want the tan function defined for x being between 90 and 270. And obviously this is in degrees, right? So it's between 90 and 270, and that's what the tan graph would do between 90 and 270. This actually goes to show the complexity of things that you can actually start to build into piecewise functions, which is, if you take a look at this, not only is this discontinuous, not only is this not defined for an entire chunk of sort of real numbers, not only does this have asymptotes, right, but it also has y values doing very, very strange things, right? Within a very short window of inputs, you've got the outputs going from negative infinity to positive infinity, and then for another window of inputs, you've got the outputs being constant, and then for an infinitely large window of inputs, so for x being less than minus 1, the outputs are just sort of positive, right? So the point is, if the formula for this sort of a graph was not actually given, if this function was not written down as such, it'd be quite hard to sort of look at this in the context of, say, a table and to actually figure out what the behavior is. So this again re-emphasizes one, the importance of actually using graphs to be able to understand functions, and two, the uniqueness that piecewise functions actually bring to the party. Before moving on, let's just quickly look at these three remarks. They're quite sort of important. So the first one says, domains do not overlap. So yeah, I would like to bring your eye to that. So if you take a look at each one of these examples I've actually got here, we don't have a case where we've got the first part of a domain and the second part of a domain overlapping, right? Because if that was the case, then you will have two functions defined on the same sort of input interval, and then that's going to cause problems basically, right? And the same thing is true here, and the same thing is true here, which is the domains are completely disjoint. Okay. The second point is only one function is defined for each domain piece, right? So for x bigger than 0, we've only got one function here. For x less than equal to 0, we've only got one function here. And again, for x bigger than 0, one function, x less than 0, one function, x less than -1, one function, and you have the picture, right? Lastly, the third remark just says freedom, right? And by that, I mean the power of piecewise functions, is very apparent from the freedom we have in being able to basically combine multiple functions to be able to define one function, right? I suppose for a lot of people, before they've actually seen this sort of thing, they actually wouldn't even contemplate the idea that actually you can have graphs looking as wacky as these and still do something sensible with them. So I suppose all this goes to show that the amount of freedom that piecewise functions bring is actually immense. Let's now think about piecewise functions and transformations for the remainder of this video. To do this in the general case, it will be sort of far too beyond the scope of the A-level syllabus, so we're actually going to do it in special case, and we're going to start by defining a special type of piecewise function, something called a modulus function. So what is a modulus function? It's a real function, a mapping, if you will, and it basically throws away the sign of a number, right? So I'm going to sort of say it casually. It throws away, put that in inverted commas, the sign. Notationally, so notation, we actually write it with sort of two vertical lines like that, or two vertical chunks of lines, right? So we might have something like, say, -2, and if -2 is put into our function, then, the function is just going to throw away the negative, so it's just going to give me +2. Right? Another example might be, say, -7. If -7 is put into the modulus function, then the output that the modulus function gives, it just throws away the sign, so it just gives me 7, right? And if I say had 4 going into the modulus function, well, it's already a positive, so there's no sign to throw away in that sense, so we just get a 4. Sometimes people also write the function as mod, right? So all of these things can be written as mod of, say, -2, and obviously that's going to be 2, mod of -7, that's just going to be 7, and the mod of 4, that's just going to be 4, right? Another nice way of defining the mod function is, say, mod means make positive. So whatever number you give it, if it's a positive, it leaves it alone. If it's a negative, it throws away the sign and makes it positive. At this stage, I should say this way of writing the modulus function is actually the convention on the A-level syllabus, right? So all the textbooks, exam papers, and pretty much anything that you're going to see where a modulus function is mentioned, you're going to have expressions looking like these sort of things on the top, right? You're not going to see the MOD way of writing this. So, in terms of a formula, right? So far you see everything I've done, a lot of it is just written in words. What would the formula for the mod function actually look like? And the point is, the modulus function is actually a piecewise function. So the way you would write it is if x is less than, say, 0, then you change the sign. But if x is bigger than or equal to 0, then you actually just leave it alone. Okay, and we can sort of check this in our case, in our first case here. So x is -2, so it's less than 0. which means the answer should be, the output should be negative of -2, but negative of -2 would actually give me +2, right? And in this case, x is -7, which is obviously less than 0, so the output of the function, this branch would apply, and it would be negative -7, which would actually give me 7. And lastly, in this case, x is 4. Well, now this branch is going to be the one that we're going to use, where x is bigger than 0. So what do we do? The branch tells me that we actually do nothing. We just leave x as x, right? So the output is going to be just 4. Okay, so that makes perfect sense. Now let's think about what the graph of the modulus function is actually going to look like. So here we see the graph of the function y equals modulus of x, and of course all we do is we plot the first function, but we only really count it for x being less than 0, and then we plot the second function and only really count it for x being bigger than or equal to 0, right? And so we have our two branches here. The dotted lines are the parts of the graph y equals x and y equals minus x respectively that we've actually not counted. So we've not counted y equals x for x negative, right? And we've not counted y equals negative x for x positive, okay? So you could see from the graph actually that all the y values are actually above the x-axis, right? Which means they're either 0 or positive. In other words, they're never negative, right? So we can just say, observe that mod x is actually bigger than or equal to 0 always, right? The other point to keep in mind would be to be observant of the fact that mod x is actually continuous. So mod x is continuous. In other words, we can draw it without lifting our pen off the page. We can just go from here to there, and then we can go from there to there to there, right? Lastly, I did want to say something just about piecewise functions in general, which is the order in which we write these out actually makes no difference. So if I actually wanted, I could easily have written, say, this the other way around. So I could have said something like this, right? That is still the modulus function, right? It doesn't change what the function actually is. But for convenience, I'll just leave it the way it is there. So before we bring this video to an end, let's just take a look at this question, which is if we're given the graph of a function, y equals f of x, how do we get the graphs of, say, the modulus of f of x, or even f of the modulus of x, right? So let's have a think about this. So what we're going to do is we're basically going to apply the definition of the modulus function. So what do we know about the modulus function? Well, the modulus function says output is actually going to be the same thing as the input, provided that the input is actually positive, and it's going to be negative input, provided that the input is actually negative, right? So this is basically the algebraic structure of what the modulus function actually says, right? Where the inputs can be any numbers and the output is of course what the modulus function throws out, right? So in other words, what I could actually say here, what I'm trying to say is output is basically equals to the modulus of the input, okay? I've deliberately written this like this so that there's no confusion as to what I'm going to say next. Now, so let's think about case 1. So case 1 is going to be f of the modulus of f of x, right? And according to sort of what we have here, the definition of the modulus function, what we're going to have, this is going to be the same thing as f of x for whenever f of x is actually positive. So in other words, for the actual graph that I have, in this case, this part here is going to be completely fine because it's positive. It's not going to change. This part here is also going to be completely fine. It's actually not going to change because f of x is positive in both those cases. However, we're going to go to the other part where f of x is negative and put a negative in front. So this is going to be the case for where f of x is actually less than 0. So the things that are actually going to change is going to be everything else. So maybe I can sort of mark that here. So that part is going to change and that part is going to change. And how is it going to change? Well, it tells me that I actually have to put a negative in front. And what happens when we put a negative in front, right? So we know a negative on the outside actually tells us that it's a reflection about the x-axis. Okay, which means that basically what's going to happen is the green part of the graph here and the green part of the graph there is actually going to get reflected. So let me maybe do that in red, and it's going to get reflected about the x-axis. So I'm going to have something like that maybe, and I'm going to have something like that maybe. So perhaps I can draw the entire graph now. I can even do this part where it was positive earlier. So this graph now that I'm drawing in red is actually the graph of modulus function of f of x. So maybe I can just write that here. So this is y equals the modulus of f of x. So we've been able to figure out in case 1 how to draw the graph of the transformed function. I've made a bit more room so we can adequately address case 2. So we're going to think about case 2 in the same way as we've actually thought about case 1, which is apply the definition of the modulus function, see what comes out, and then see if we can use one of the laws of transformations that we already know to be able to sketch the graph of the new function. So let's do that. So in this case, we're going to have f of x is obviously f of modulus of x, I should say. It's going to be equal to, well, it's going to be equal to f of x for whenever x is positive. So that's not going to change, but it's going to be f of negative x for whenever x is actually negative, right? So again, applying the same sort of reasoning, but perhaps sort of using slightly different colors. So I come back here and I say, well, whenever x is positive, I want just my function f of x. So x is positive for all this part, right? So I just want f of x unchanged for all of that part. Now it doesn't really matter whether f of x itself is positive or negative on all that part. The important thing is that x is positive on all that part, right? That's what happens when we apply the definition of the modulus function in case 2. So, so that's that. But then if we look carefully what's being said about the second case, the second case is whenever x is actually negative, we don't want to draw f of x, we actually want to draw f of negative x, right? And what does negative on the inside do? Well, that does a reflection in the y-axis, right? So I'm actually not going to have any of this. I'm actually going to have a reflection in the y-axis of this part here actually put on this side, okay? So let me write that down first and then I'll sort of draw the graph, right? So I'll say negative on the inside implies reflection about y-axis. Okay, so what we're going to have is we're going to have the same sort of thing on the right-hand side now on the left-hand side. So it's going to be something like so, and then it's going to just sort of shoot up. This is not a very good sketch, but I hope you see what the point is. And of course, so if I want the graph of the entire thing, I can actually also color in the part on the right-hand side as red as well. So that's now the graph of our f of modulus of x function, okay? Now the important thing I should say here is it really does matter what part of the blue graph you actually reflect, right? So according to the definition of the modulus function being on the inside, you've got to reflect the right-hand part of your blue graph into the left-hand side, right? If you reflect the left-hand side into the right-hand side, I should say that's not quite f of the modulus of x, that will actually be f of the negative of the modulus of x, okay? So you've got to be careful about that. But I'll sort of leave that to yourself to work out the details. And with that, I'd like to bring this video to an end. Thank you for watching. We hope you found this video useful. If you did, please hit the like and subscribe buttons. It's a great way for sort of new people to find the content. And also do leave a comment to let us know what you would like to see more videos on. We will see you in the next video. Thank you for watching.